Motion is common to everything in the universe. We talk, run, and ride a bicycle. Even when we are sleeping, air moves into and out of our lungs, and blood flows in our articles and veins. We see leaves falling from trees and water flowing down a dam. Automobiles and planes carry people from one place to another. The Earth rotates once every 24 hours and revolves around the Sun once in a year. The Sun itself is in motion in the Milky Way, which is again moving within its local group of galaxies. Motion is change in position of an object with time. How does the position change with time? In this chapter, we shall learn how to describe motion. For this, we develop the concept of velocity and acceleration. We shall confine ourselves to the study of the motion of object along a straight line, also known as rectilinear motion. For the case of rectilinear motion with uniform acceleration, a set of simple equations can be obtained. Finally, to understand the relative nature of motion, we introduce the concept of relative velocity. In our discussions, we shall treat the objects in motion as point objects. The approximation is valid so far as the size of the object is much smaller than the distance it moves in a reasonable duration of time. In good number of situations in real life, the size of objects can be neglected and they can be considered as point-like objects without much error. In kinematics, we study ways to describe motion without going into the cause of motion. What cause motion described in this chapter and the next chapter forms the subject matter of chapter 4. The average velocity tells us how fast an object has been moving over a given time interval but does not tell us how fast it moves at different instant of time during that interval. For this we define instantaneous velocity or simple velocity v at an instant t. The velocity of an instant is defined as the limit of the average velocity as the time interval delta t becomes infinitesimally small. In other words, where the symbol stands for the operation taking limit as of the quantity on its right. The language of calculus, the quantity of the right hand side is the differential coefficient of x with respect to t and is denoted by dx by dt. We can use for obtaining value of velocity at an instant either geographically or numerically. Suppose that we want to obtain geographically the value of velocity at time t is equal to 4s for motion of the car represented in figure 2.1 calculation. Let us take delta t is equal to 2s center at t is equal to 4s. Then by the definition of the average velocity, the slope of time p1 p2 gives the value of average velocity over the interval 3s to 5s. Now we decrease the value of delta t and 2 second to 1 second, then line p1 p2 becomes q1 q2 and its slope gives the value of the average velocity of the interval 3.5 second to 4.5 second. In the limit delta t, the line p1 p2 becomes tangent to the position line curve at the same point p, and the velocity is equal to 4s is given by the slope of tangent that point. It is difficult to show the process graphically, but we have to numerical method to obtain the value of the velocity. The meaning of the limit process becomes clear. For the graph showing in figure 2.1, x is equal to 0.8 t3. The sixth column list the sixth column list of the difference delta x equal to xt minus x2, and the last column gives the ratio of delta x and delta t, that is the average velocity corresponding to the value of delta t listed in the first column. Instantaneous speed or speed is the magnitude of velocity. Example, a velocity t plus 24.0 milli per second and velocity of minus 24.0 milli per second both have associated speed of 24.0 milli per second. It should not it should be noted that though average speed over a finite interval of time is greater than or equal to magnitude of the average velocity, instantaneous speed at an instant is equal to the magnitude of the instantaneous velocity that instant. Why so? The velocity of an object in general changes during its course of motion. How to describe this change? Should it be described as the rate of the change of in velocity with distance or with time? This was a problem even in Galileo's time. It was time thought that is that this change could be described by the rate of change of velocity with time, but through the through his studies of motion of freely falling object and motion of object on an inclined plane, Galileo concluded that the rate of change of velocity with the time is constant of motion for all objects in free fall. On the other hand, the change in velocity with distance is not constant. It decreases